Today we're going to be discussing the grammar of graphics. And so I'm just going to give you a quick overview of it, and then I'm going to spend most of my time going through some examples, so you have an idea of what this is like. So a grammar of graphics, that might be sort of a different expression than you're used to. This was a result to try and describe a graphic. So the grammar came out of asking the sort of questions like, what is a graphics, and how can we succinctly describe a graphic, and how can we create the graphics we've described? Grammar, of course, English isn't a grammar, but it also has a definition as the principle or rules of an art, science, or technique, with the idea that a good grammar would allow us to gain insight into the composition of complicated graphics, would reveal unexpected connections between seemingly different graphics, provide a strong foundation for understanding a diverse range of graphics, and guide us on what a well-formed or correct graphics looks like. I understand there's some theories too, or questions about the connection between language and the way we actually think, and how that influences our thinking. So the idea of a good grammar for graphics should be something that assists us. It doesn't get in our way. It's very expressive, and it lets us, it really assists with our generation of graphics. So there's been a couple papers published on this, going back to the original 83 with the semiology of graphics. And then there's a significant book, The Grammar of Graphics, which sort of laid the foundations. And then in 2010, there was Wickham, who is sort of the R programming language fame, came and wrote up the layered grammar of graphics and produced the implementation of the ggplot. So what does this grammar look like? Well, here is our example. This is with the R. So we have an underlying call to the ggplot routine. So the grammar lets us sort of describe the graphics, and we have a basic function here where we can give it our data, and then we add what we call geometry functions. We'll be looking at this, that add graphics to it, so lines and points and bars and all those sort of things. And then we can add coordinate stuff. We can add stuff for faceting and for adjusting our scales, and guides. So guides would be things like text annotations and stuff, and also comes with a theming system. And we just add these all with the plus operation. So we can specify as much or as little of these as we want. And based on our data, it makes intelligent guesses as to what the rest of this is. And then we can come along and tweak it later. So it's a bit, I guess, like an English language too, right? Where you can make sort of a basic statement, or you can go into a lot of detail. So, and here I just talk about them. So data would be our underlying data. And well, we'll be discussing these here as we go through them. Now, there is some implementations of this. The longest standing one was the ggplot, and specifically version 2, coming out of Haley's original work. So that's you can get that, the ggplot tidyverse. And then more recently, Python has implemented a version called plotnine, which is pretty much an exact duplicate of the ggplot. So all the Python fans there, you can use it. I've used it as well. It's a very good book. I mean, very good implementation. And now there's various 2 R sets of R books that Haley and the tidyverse people have put together. So there's ggplot2 elegant graphics for data analysis, which goes into all the details. And this is an excellent reference for the R implementation too. I mean, sorry, the Python implementation too, because it's almost exact copy of that. And then there is R for data scientists as well. So this one here also touches on the rest of the sort of tidyverse package, but it speaks significantly to the graphing one as well. And these books here they're open source, so you can actually go to GitHub and submit pull requests if you want. You can view them online, or they've been printed too through O'Reilly, and you can buy them on Amazon. So now without further ado, let's just dig into this because this is probably the best way to sort of understand this stuff. So this for just have some data, R comes with a whole bunch of various data sets. I'm going to be doing all the examples in R, but you can do them in plotnine, very easy to translate directly over. So first of all, I've got my R running on the right-hand side, and I'm just going to load up the tidyverse library set, which includes ggplot2. There we go. And with that, we get access to the MPG, mile per gallon data set. And the mile per gallon data set is just a collection of data from the US Environmental Protection Agency, a subset for the years 1999 and 2008, as you can see here by the year. And it's just got a list of cars, some details about those cars and their fuel economy in miles per gallon. So the city fuel economy and the highway fuel economy. So we have the manufacturer, the model, the engine displacement, the year, the number of cylinders, the transmission type, the drivetrain, so front wheel drive, four wheel drive, we can see there, city, highway, the fuel, most of these are petrol, and the class, what's compact, subcompact, SUV, and so on. So this might be typical of some sort of example data that we might want to be looking at, and it's certainly good enough to start generating some plots. So without further ado, here's the first plot I'd like to create, which is just a simple plot of the engine displacement against the highway miles per gallon. And we'd sort of expect as we get bigger and bigger engines that, you know, the miles per gallon, the fuel economy is going to start dropping off, which is what we kind of see in this graph. So let me just generate this graph. So the basic command to generate a graph is called a ggplot. And ggplot gives you a graphics object, which when you print it, it pops up a window that displays the plot. And it also has an overridden operator plus, so you can add the additional stuff you want to it. And it also sets the data for the other functions, the defaults for the other functions. So you can specify anything you can specify to the other functions. Generally, you can specify to ggplot, and then that becomes the default. Usually, all the stuff we want to add has the same data. That's not always the case, but usually it is. So we just stick that into the ggplot. So if I just do this here, this pops open a window of my plot. And so there's nothing to this plot so far, but let us add to that. So we're going to take that basic one, and then we're going to add some point. So we're going to add a geometry. There's a large class of geometries here. You can see if I press tab completion on my system here, I have a large class of all sorts of areas, blanks, bars, box plot, dot, maps, rectangles, segments, violins, smooth text. In our case, we're just going to use the point geometry. And then the point geometry takes a variety of options. The most significant one is the mapping, and the mapping specifies how to get from this information here, how that gets mapped onto the properties of the point in order to show up on my graph. In this case here, it's pretty simple. So the mapping is going to be, they call it an aesthetic. So the mapping the aesthetics, or mapping to our aesthetics, is going to be the X value. If we're going to just take as the displacement, if you remember right across the bottom of this one here, so displacement, and the Y value we're going to take as the highway miles per gallon. And it helps if I spell displacement right according to what I have in my chart. There we go. And this aesthetics function is actually, it does some special things here, so I don't have to put quotation marks around these values and stuff. And so if I was running the Python, you can't actually have quite as nice a syntax here because limitations of the language. So I'd have to put quotation marks around these variables. I'd say x equals displacement in quotation and y equals highway in quotations, but that would be pretty much, oh, and yeah, data equals mpg. Mpg is actually a value. So that's pretty much would be the only difference there. And now you can see I have my plot here has shown up. I'm just going to resize this. These plots are, of course, dynamically adjusted to, as you adjust the screen here, it'll automatically adjust the layout there, as you can see. So anyways, that's the first sort of basic plot we have. Let's go talk about our next plot now. And of course, before I get on to our next plot here, as I said, the ggplot function itself sets the details. So this would be perfectly valid to have specified the data over here. Data equals mpg. That generates the exact same plot. It's just as you remember when I originally showed you, you add a whole bunch of specifications to it. And so a lot of those functions you add, they'll be using the same data set or they'll have common attributes. So it's just a lot easier to put it into the ggplot function. So here we are looking at the next mapping. And basically I've specified another aesthetic. So originally we just had the X and the Y location, but if we actually look at this geom_point function here, it has a lot of various aesthetics you can specify. So I'll just bring up the help for geom_point. Cool. So we can specify the X, we can map to the X value, the Y value from our data, the alpha value, so the transparency level, the color, the fill, a group is a grouping parameter that doesn't actually get displayed, the shape, the size, the stroke are all various attributes that we can change about these points in order to convey information from our data. So the next thing I've suggested here basically is we're going to set the color. And you'll notice this here is the Canadian, actually the British spelling, I guess, which is also the Canadian. It also accepts the American is fine as well. C-O-L-O-R if you prefer. So here we are. In this example here, we've just redone it and we've set the color equal to the class. So let's just redo this here again. We'll just go back up here. So we've got X is the displacement, Y is the highway, and we can add in the color we want to come from the class. And that gives me this graph here. And you can see ggplot, as I said, like you can control all this here. This is sort of information and legends and stuff. It looks at class and it looks through my class here in my data. And it sees that these are character sets, so it assumes they're discrete variables, and it gives me a discrete legend here. If I'd used something like the displacement or the highway kilometers and stuff, it would recognize that as double or integer quantities, that those are, or I think displacement would be a good example. As a double, it would recognize that as a continuous, and it would pick a continuous scale here with like a sliding a color scale that goes from one color to another color. And same along here is the X position. It's recognized I've mapped that to display a continuous variable. So it's given me a continuous, can't think of what these are called, continuous scale along the bottom, I guess, for lack of a better word. If I had a discrete variable, then I would get just various classifications marked off. And you can override all that, of course, but it makes a lot of, it allows you to get a pretty good original graph off of very short specification. So I guess much like a regular language, there's a lot that can be read into and assumed in a statement, and ggplot does that. So let's have another look at our next map. Oh, sorry, here we go. In this case here, so one of the problems with this graph here actually is it does a poor job at representing fuel economy, and that's because it compresses all the bad fuel economy down here in the bottom range. A much more reasonable rating would be sort of with the rest of the real juices, which would be gallons, or usually it's liters per 100 kilometer, or in this case, since our units of this, it could be gallons per 100 miles. So we can do that as well. So we can actually put equations directly into these ones here. So these here are expressions that are evaluated in the context of your data. In this case here, we just said, so it brings us, for each row of this data, it brings all the values into scope, and then it evaluates this expression. So this can actually be a complete formula. So for example, we can say, okay, well, let's change that to 100, divide by the highway in order to get gallons per 100 mile. And we'll replot this. And you can see it also takes what I've specified there and assigns it as the default label. And now with this change, I have blown out a lot of the differences we could see down in the bottom here too. And I mean, one of the interesting things about our original data too was we had these vehicles here that had big displacements, but still reasonably good fuel economy. And with our class here now, we can see these are all two-seaters. So likely these are, sports cars with big engines. And these guys up here are kind of what we'd expect, which are pickups and SUVs. And then we can see like the really poor performers here, where before under the old graph, those were all squished up into the bottom range. Here you can actually see there's a fairly significant, the worst performer here doesn't look like too much difference, but up here you can see a much greater difference. Anyways, all very easy to plot with ggplot. And of course, I can combine things here too. I could say y is equal to, I don't know, displacement times the number of cylinders divided by the city fuel economy. That wouldn't make much sense for this graph, but for some other graph, that might be a reasonable thing to do. Now, one of my favorite features of ggplot is the good support for faceting. So faceting lets you quickly break things out to see sort of patterns. And it takes an underlying graph like this one here we've been looking at, and it allows us to break them out into identical graphs that share the same scale ranges. So in this case, I've taken this graph here and I've faceted it by manufacturer. So I can see all of Audi's cars separate from the Chevrolet cars, separated from Dodge cars, separate from Ford cars. So that is a super useful technique of just having that initial look into your data. And it's also super easy to do. To do that, we just add to our definition a faceting bit. I'll just actually put these on separate lines. So in this case, we just add a faceting object to this. So there's a variety of facets, as you can see here. If I press tab, we can put them in a grid or a wrap or a null. And this, so you can have, by putting them in a grid, you can have two faceted variables, one along the top and one along the bottom. In this case, we're just faceting by one variable, so we just want it to fill as many columns as it can, and then it naturally wraps to the next row. So we're just going to use the wrap facet. And so we specify what our facets are. Facet is equal to the variables. So you can facet on multiple variables as well, but I'm just going to facet on the manufacturer in this case. And now here, I also have to specify what my data is. So my data is miles per gallon. But rather than each specifying the data in each of these functions, it makes much more sense to just specify that once. So that's where I start sticking common stuff into the ggplot, or initial ggplot, to set the defaults for the other functions. All right, so I'll run that. And you can see here now we have this faceted out. We can see Honda tends to make small fuel efficient cars, and probably not too surprising, a lot of your American manufacturers here have a lot of heavy SUVs. So anyways, faceting is a great way because you get those locked scales so that you can easily compare between them. And so if you're doing some sort of inference or trying to figure some stuff out, that's a wonderful feature. And it's super easy. Now, so far, we have just been talking about one geometric object here. We've been having the points. You can add any number of geometric objects to your graph. And then they will be plotted there. So this is another example here where we've also included, in addition to the fuel economy, we've included some sort of fit to sort of show us where the trend is. You can, of course, it's R, so there's a lot of statistical options for what type of fit you want. I believe this might be some sort of spline fit, but super easy to do here if we just go back up to the right window. So we'll go back to this one here. I'll just put these again on separate lines to sort of, and you can assign them to variables too. So I can say like P equals ggplot, and then I can do P plus geom point, and then P plus, so you can just slowly build them up that way. In this case, so we got the geometry object there, and then we're going to add in the another geometry. Let's put the data up here too, because we don't want to have to specify that on every line. Just specify the data once. And then the geometry we're going to add here is a smooth line as well. So we'll add a smooth. And the mapping for the smooth is going to be the aesthetic. I'm going to map the aesthetics to, well, these are the exact same here. So in this case here, actually, if I wanted to, because this mapping has the same underlying aesthetics here, I could even push these up into here to specify this simpler. So mapping equals aesthetic. We'll just specify the X and Y. And then the only thing special is this one here has a color class. Also adds a color. There we go. Let's plot this. Oh, and hold on there. I see I've actually made a mistype bracket level there. There we go. Run that. So the geometry smooth is using this LOESS method to do its smoothing. And it's smoothing on Y as a function of X. And so here we have this graph here. And a lot of the, people use ggplot and they're like, oh, where's the function to do like air blocks or box plots or something? And they're because we're used to thinking of each plot has its own function, but in ggplot, if we want box plot, then we stick our points on, and then we add a box or airline. So we build up our display, our graph. So you have to think of just all the various points that go into generating that, right? You add some whiskers to your scatter data, and you add some boxes, and then you've got a box plot with the whiskers on it. And as I said, there is an amazing number of different geometries here that are supported. Okay, so let's have a look at another graph. So in this case here, I want to talk about statistical transformations. If you remember, right, if we go back there to the start, there was a huge number of things. We started with a ggplot, and then we added geometric objects. We can also do statistical transformations in showing our data. In this case here, as we're summing up the number of vehicles in each class, and then we're doing a plot of that. So how would we do this? So that would just be a ggplot again. We start with our plot. Again, the data for all our stuff we want is just this MPG. You would use, if you had multiple data sources, that's when you would start passing them, specifying the data to the individual geometries. So then we're going to add to that a bar geometry. And for the mapping, we are going to get the aesthetics for our bar from X. So the X position here is going to be the class. This comes back to what I was saying earlier. When ggplot looks at this, it'll say, oh, the class is not, it takes on discrete quantities. It's not a continuous variable, so it'll change these just to a labeled axis. A discrete axis as opposed to a continuous axis. That just happens automatically. And for the fill value here, so basically the fill is going to be the drivetrain. So we have the two drivetrains or three drivetrains we'd mentioned before. So we have the four-wheel drive, the front-wheel drive, and the wheel drive. If I hadn't specified the drivetrain here, these would just be standard boxes without any sort of color in them. So there we go. And so now we have this plot. This one here is a little different in that it had the stroke. I'd put a black outline on the stroke. We can easily add that in because that brings up another sort of interesting feature of these ones here. So you can, all these attributes, so if I look up the geometry bar, it has various attributes such as the X position and the, what color it's filled by. And also it has the color that's used to draw the boxes around it. You can map these all from your data. You can also, if you want to override their defaults, just specify a global value. So in this case, I can say, well, and put around those the color equal to black. So when I'm assigning it a constant value, it's not part of the aesthetics masking. I just pass it in as another value. Property, and now I've got the black stroke pen lines around my boxes. Again, each of these functions you can look up to see exactly what sort of options there all is. So we have the X, the Y, the alpha, the color, the fill, the group, the line type, the size. So, if I wanted to here, I could, let's go back to the function here. I could easily plot this too. I could say, okay, well, the color, and let's set the alpha value equal to 0.5, for example. So I've made them 50% transparent. Or I could set the alpha value from some sort of data parameter. I could set the alpha equal to something to do with the displacement. And then it'll add another grid on here that maps the displacement values onto alpha values, and it'll chop these up additionally to also display that sort of information. So one of the other things we saw was a position adjustment. Oh, before I talk about the position adjustment here, let's just go back to the statistical transformation here. You might be wondering where this statistical transformation came. I mean, obviously it did the summation from the bar. And that's because all the geom objects, if we actually look into their definition here, they have a stats function that they go through. Most of the stats like so this case, the default statistic is count. So it applies count. So first of all, it groups the data according to all the things I have mapped by my aesthetics. So it breaks them all out according to that. And then it passes each of those groups through the stats to do some sort of summary stats on it. Now, something like the position geometry, the stat is just the identity function. So it just leaves that data alone and it comes on through and then it plots the points. For something like the bar, the default statistic is count. Now we could put anything else we wanted. And we can say, okay, I don't want the counts. I want to see the averages. I want to see the means. I want to see the medians, sort of whatever you want. So that's where the stat came in. And if you actually look into the ggplot library, it also has there's also stat functions you can add as well. So just like there's a geom bar, there is a stat count function. There we go. And each stat count, actually this is on the same help page. So if you look, here's the geom bar, scroll down, there's a stat count. And a stat count is just the opposite way of specifying it. So what you want to use is sort of up to you. A stat is a specification of the statistic you want, and then associated with it, it has a default geometry it uses to see it. So you can see this is just another specification of the same thing, the stat count, and we're going to show it by default with the bar geometry, or we can specify it this way up here if we want. We're going to have a bar geometry, and the stat we're going to use to pre-filter our data is the count. So we can generate this plot equally good either way. Let me just go back up here to, here we are. So we could easily also have said, well, we want the stat count, who has the default geometry is the bar, and then everything else remains the same. And that's, of course, gives me the exact same graph. So which one of those you use just sort of depends on sort of where your focus is. Generally the one whose parameters you want to change, you specify on the outside, because the internal one is kind of a pain. You can do it, but to specify changes to actually like the statistic function. You can also define your own statistic function, so you can put your own personal function in here instead of count. Count is just an R function that gets called. If I look up count, lets you quickly count the unique values of one or more variables. So just a regular R function, you can specify that. Yeah, so all the data goes through a statistic layer. For most of the geometries and such, like geom point, that statistics is the identity function, so it does nothing. Now it also goes through a position function, which tweaks the positions, and for most of them these are as identity as well, but you can use that to say unstack these bars and display them side by side, which will be the next example I'm going to show you guys. Exit all this help stuff. There we go. So in this case here, now I'm using a position adjustment to, instead of having these bars stacked on top of them, I'm moving them out to be side by side. So geom bar, I guess we don't really need it. I don't really care if that alpha is in there. All right, so I'll add again another one. Oh, sorry. No, the position parameter was passed to the geometry bar for matter. So instead of the position equaling the default identity, I'm going to override that, and I'm going to specify the jitter function. And if you look up jitter, what it does is it moves them so they're no longer overlapping with each other. Sorry, not jitter. Jitter adds a random amount of movement to them in order to break out points. That's useful if you have a whole bunch of points overlaying a little bit of random Gaussian noise. So that's not what we wanted for this bar. Instead, what I wanted was to to adjust their positions with the dodge function, which moves them so they're not overlapping each other. So there we go. So this dodged them to make them not overlap with each other. I mean, the sort of amazing thing is they generate all these different graphs just using the same thing, but this speaks again to the power of having a good underlying theoretical underpinnings with the grammar graphics and the work that's been done there. So let's go back here for this next one to our, just scroll back through these here, to our geometries. So I believe this graph is this one. Yes. And except for this one here, you can notice like down here, we don't see the clustered ones. I mean, if I can sort of see this magenta colored dot here has a tiny bit of blue outline, which kind of suggests to me there's multiple ones lying on top of each other. But up here, I can see what I've done is I've applied that jitter function, which is the one I accidentally applied to the bar graph. And that just adds a bit of random Gaussian noise in order to move plot points that are sitting on top of each other off of each other so you can see them. So that's an example of when you might want to use the jitter routine. So let's do that here. So we'll just add into here, we'll say the position, instead of using the positions as given, we're going to run them through the jitter function. And now you can see these ones here that were overlapping are now, we can actually, this gives us a bit of idea of to what the density is, where the original graph, that sort of information was hidden because they're overlapping. So, I mean, interestingly enough, this is an example of where making the information conveyed is slightly less accurate because it's got that additional bit of noise, but it does visually give us more information. So here's another example. So far, we've been using the rectangular coordinate system. We can, of course, add a different coordinate system if you want. This would be a circular coordinate system you can use it for doing pie charts and this sort of thing. In this case, this is what they call a wild rose because it also, not only is it got divisions according to the pie chart, but it also varies the height. This is basically just that bar chart we saw before, except for now it's wrapped onto circular coordinates instead of other ones. Ironically, these graphs are kind of like, wow, that really looks fancy, but they do a really lousy job of conveying information. People have a very hard time sort of identifying areas of equal information. So this graph does a lot worse job than the bar chart of actually conveying what the underlying information is, despite looking much cooler. So not recommended at all, but it's something that you can do easily with R. So we just take our regular function here. We'll go back up to the geom bar here. Now these are stacked, so we're no longer dodging the positions, although, I mean, you could do that too if you wanted that sort of polar coordinate view. And so then to this here, we're just going to override the default coordinate system by sticking in some polar coordinates, and that's all it takes to make a polar plot. So again, this again comes to the same sort of thing, right? Like if you used other plotting libraries, we were like, oh, where's the polar plot functions? Well, in this here, it's the grammar graphics, so it's describing the graphics. You just, all I'm doing is everything else remains the same. I'm just altering what the final mapping of the coordinates are onto the display. So there is the rows. Now, by default, it's added a little bit of space between the graphs to help break them out. That I can easily remove. I will just go back up here and I will make this geometry bar here. I will set the width equal to 1 for 100% in order to remove that a little bit of space in between there. And there we go. We've got a fancy pie chart, which does a really bad job at conveying information, but looks really cool. So, Now, we can start customizing, right? So I mean, this is the nice thing about ggplot, is super easy to get in there and start looking at your data right away. You know, typically you'll do like you add some geometry points, and then maybe the first thing, you don't really care that your labels aren't, you know, only make sense to you. This is not a production quality one, and it's just picking these classes here from which you're seeing, and maybe the color selection isn't that great, but you've got your data up there and you can factor it right away to start seeing how different groups compare and stuff. But at some point you start wanting to clean it up here a bit. Okay, so let's talk about some scales and labels. So this is getting into sort of customizing it for for something you'd actually want to stick in your paper or something like that. So if we're going back here again to just the standard plot there, so I'll scroll myself back to this one here. So what we can do to this is we can add to it a scale. So if I just plot this as is, let's just bring it back up here again. It uses the default scales. So the scales are the things it shows, and I'll just show you over here so I don't bring that other window up. This is considered a scale, as are considered these, as are considered these. So the scales show you the mappings from the range of values to the aesthetic. In this case here, here's the range of values, and the aesthetic, associated aesthetic is the color. Here's the range of displacements. The associated aesthetic is the X position. Here's the range of 100 divided by the highway, and the range of values, again, the aesthetic is the Y position. So it generates default ones. So this one here, basically, you can see down below, I've got the default color scale it's using, and I can override that. So if I go back, oh, shoot. So we'll go back to our plot here, and we're just going to specify one instead of it picking one for us. So we can add into this here. We can say, okay, well, let's use the scale, the color Brewer scale, which is an ideal. If you go on the web, there's a lot of research done into what are ideal scales. A large number of people have some degree of color blindness. There's you know, questions of whether colors how different colors look, do those map well to how different the underlying values are? And there's a lot of problems with just using the sort of the default hue kind of color wheel most people use. So they make some good ones, good assumptions. So the color brew scale is a good choice for discrete data, prints well. Another question is, will you print it in black and white? Is it still indicative? Like, is that shade of green when it comes out in black and white comparable to the shade of yellow, or do they all just look like the same amount? They all look like some level of gray. So lots of people have done lots of heavy duty thinking about this and come up with some very good selection of colors. So Color Brewer is one of them. I'm using the qualitative Color Brewer scale, but there's a whole ton of scales and color scales and options there. So I mean, here, let me bring up the scale. So you can see there's a massive amount of scale functions. And if I want to look at particularly the color scale functions, avail both as COL and COLOUR again. So I have a large number of built-in color scales I can choose from. Common ones, the brewer and the fermenter, are very popular ones you can see online. And of course, you also have the standard hue, which is used by a lot of packages, but is not a very good one to pick. So there, I've changed the color scale. Of course, now the default scales here along the axes are linear so far, but we can easily change that to be a log scale. So let's have a look at that. So go back up to our example here. So say we want to change the Y to being a log scale, which would also help us. So originally we switched to 100 over highway in order to blow out that lower dynamic range there that had, to be able to distinguish well between something that had like 0.5 miles to the gallon and 0.3 miles to the gallon. If you're looking at what looks like 5 miles to the gallon versus 10 miles to the gallon are very physically close on the screen, even though, that's 5 miles to the gallon is twice the badness in fuel economy. Meanwhile, if you look up at the top, going from 30 to 40 miles to the gallon is a huge jump on the graph, even though that doesn't represent that significant of an increase in fuel economy. So that's why we switched to the alternative view where we were looking at gallons per kilometer. Another way we could do it is we could put it on a log plot. So then a log plot basically would transform equal multiples into equal spacing. So super easy to do. All we have to do is override the default. So we'll add to this here. We'll add a scale. We're going to say why we want that in logarithmic. Log 10. There we can see, and now you can see the bottom there from the bottom range at 20 there is now taking up a lot more space. So now we can see that just how horrible those cars are at the bottom and make a comparison relative to the improvements at the top. So that's another way of fixing the fact that miles per gallon is a bad sort of thing to be looking at in order to determine your fuel economy. I mean, the things we want to really know is the fuel economy twice as good, half as good? We want a relative comparison, not an absolute. So logarithms give us a relative comparison. And so super easy to do in ggplot. Now, if we want here, so let's just stick back with our original one, which is 100 gallons per 100 miles. And I'll just give you another example here. So we might want to, for example, change these labels on the side there. So the color brewer scale there has 2-seater compact mid-size minivan, which is just pulling from our data, which is would not be something you'd actually want in a production graph. So we can easily change these. We can specify what the labels are. So C and R is just a way of creating an array. So now I've got decent titles on that. I probably want to add some actual labels onto the graph too. So there's a nice function they have here. We'll just add another addition to the specification of this graph here. So we'll there's a labels one that lets you set a lot of the labels. So let's say the title would be equal to, we might want to change what my x-axis says. So say the x here, instead of just this, we will say engine displacement. And we might want to change what the y-axis here is. So I'll just put these on their own line. Say the y-axis, instead of saying 100 divided by highway, I'll say gallons per 100 miles. And it's the whole sort of grammar thing is just like, you write your rough draft of your paper, whatever, and then you fill in details and you correct your spelling and stuff and just really sort of polish it up. So here we are back at the final scale I wanted to show you there. And then the final thing I want to show you, so I'm sorry here, I'm just going over slightly with interruptions, is it's also themable. So the themable controls just the non-data appearances, and there's a wide variety of themes you can choose for and customizations you can do with the themes. So for example, this one here, I forget what the name of the default theme is, but I can super easily change that here. Let's just go back up to my statement. So I can add to this a theme element. And I can say I want to use a minimal theme. instead. So it's like skins on a, so it's taking out a lot of the borders. It's so of course the theme minimal is to be sort of almost Apple kind of like looking desktop. So that's what we got. And so there's a whole bunch of themes you can choose from. Black and white, gray, classic, light, dark, up, more minimal, void. And you can also create your own themes, put together your own themes. You can specify a theme function as well to just make specific tweaks to an existing theme. So if we go back up here to my example here again, we can say, okay, we want the minimal theme. And then we're going to do some tweaking on the themes as well. So we'll add a theme call. And for example, as you can see, my legend in my example here is on the right, where in there it's in the upper left. So I can fix that if I want. And you can just look into the documentation for the theme. It tells you all the various massive amount of stuff you can set. So we're going to set the legend justification equal to, we're going to stick that into, so on the left side will be the left right justification. And on the top, there we go. And then we're going to also tweak the position here. Legend dot position equals 25 and 0.925. So these are just relative screen coordinates with 0 and 1 being the full length across however much the graph is stretched out. And with those two there, we push that up into the other thing. And I can see I haven't actually, I forgot to change the, oops, sorry, moving mouse, or I forgot to change the top here, the information on the actual specification on the legend, but I could easily do that as well. I can just say, I guess I might as well, just to have done it. We can go back into here and our labels. We'll add a label for the color specification as well. So new line here, and the label we want on the color. The color legend is just going to say vehicle class. Vehicle class. And I've got a bracket error because my R did not come back. Oh, here it is. It should have been a comma, not a quote. Just have to try that again. Comma. And I accidentally pressed the backslash, and there we go. All right, so that's got it. I mean, this one here, I had added a subtitle as well, MPG data set, but I think you've probably seen enough. So creativity, I was going to show you this plot. This is another plot. This probably looks quite a bit unlike other plots you've seen. And it's just a factor. It was some default overridings to break it out to group by, we're grouping by the car manufacturer, and it's showing all their models, and then it's plotting the different fuel performances on a thing. So this is a relatively simple factor specification to generate that. So in the ggplot, you have to stop thinking of, okay, how do I make this? What's the function for this specific graph? It's how do I compose all the stuff together to give me the graph I want? So that's all I had to say. I hope this has sort of whet your appetite for ggplot. It's definitely my favorite 2D plotting routine, and graphics library. I use both the Python and the R version. And it's just super great for digging into your data, and then also for polishing it up to the point you want to include it in your papers. So that completes the webinar.